is now going to do a presentation on the Universal Rewrite System, URS, and I'm co-presenter, so I will occasionally say things, perhaps. We'll see how it goes. Okay? I'm also chairman. You know,
many hats.
Pooh-Bah, yeah.
Okay.
Go ahead, Sid.
So I'm going to use a biology analogy for the URS. It's not exact. It's just a way to think about it. It's not anything that you need to take literally. This presentation is a work in progress. We've had many different previous papers and interpretations. As you can see here, we've got the Dirac interpretation of a particular order in the URS. Then we've got all the other ones like the physics, the genetic interpretation, and the mathematical interpretation in terms of Clifford algebra. So I'm going to talk about another URS phenotype that will be mentioned in this presentation. So in formal language theory, which is I'm taking as a subfield of computing theory that provides the languages that are inputs to the state machines. I'm assuming a lot here right now, but just bear with me. I'm going to say the URS is expressed phenotypically as a certain language accepted by a specific Turing machine. And that language is, as you can see right here, a particular form that starts at 0 and goes on forever. The Turing machine that accepts that URS is this one. And this is from a diagram from Michael Sipser, Theory of Computation. I believe that's his first name, but you can check that. I can put more references in if you ask me. This work was motivated by two papers that I've co-authored with Peter. And these are a couple abstracts from those two papers. The first paper, as you can see, we're basically setting out that the URS is the meta pattern of the universe. I know it's a big claim. And its first formulation we found, well, not first formulation, the formulation I've introduced or found, well, we both kind of come up with, is as a formal language theory around the semantic unit of that is centered around a 0 word. So this would look like what we would call a 0 word right here. It has a positive character and a negative character. I'm taking hash as a negative character. In that paper we talk more about the different acceptance machines that accept this language, and you can read all about it. And the second paper is just more applications and what can be developed with it. But the first paper is the theory. So the URS as a language, in formal language theory, I'm going to use this analogy, this description now, are any set of strings over an alphabet. That should be URS, not UXS. So as a language, I'm taking it to be an infinite number of zero totality words or empty strings. Syntactically, using standard Western alphanumeric symbols, a zero totality word will be generically defined as this, where this is where I've already mentioned it's a positive and negative character. So semantically, this sums to nothing or 0. So I'm taking all the positive characters, I'm taking all the positive half of the rewrite system and representing it, condensing it into this single symbol, and then likewise with the negative. And I'm saying that in a nutshell, you can define the syntax and semantics of the URS as a formal language using this equation. And I'm taking addition as both, the plus sign is addition and concatenation as well. I'm going to speed up. Now, we've already talked about the Clifford algebra phenotype, and that is pretty involved. So I will just let you read this. And this is Clifford's theorem that basically says in one theorem what the Clifford algebra phenotype of the URS is like. I'm going to just skip through that because I've only got a limited amount of time. I want to point out here that only certain Clifford algebras compose the URS. It's very specific. It's not just any Clifford algebra. And these are the ones for the first 6 orders.
can I point out here, if you want something you're familiar with, you're starting off here with real numbers, and then you've got the first set of quaternions, second set of quaternions, and incomplete set of quaternions or complex numbers. So it's a complex double quaternion algebra that we think is the most important thing. It happens to be the same as the Dirac algebra.
Okay, the URS can be thought as being built. Okay, so we've got, how do we build things in the URS? Well, we use, in the Rowlands literature, it's called the conserve and create. I will tell you that, Peter, do you want to say anything about this?
Yeah, basically, you do this process. You conserve whatever the alphabet is, anything part of it, concatenated with the alphabet, only gives you the alphabet. But if you do the alphabet concatenated with itself, you get a new one. That's enough said.
Okay. Okay, now here's a concept that I might get my head chewed off because I'm using
well, this is just standard quaternions.
Standard quaternions, and I'm saying here that this is a nice set theoretical intersection representation if you take the length of the quaternions. And when I say length, I mean the minimum generating set of the quaternions as the symbols A and B generically. A and B is I, J, or whatever. And yeah, so that's that. And there's a corresponding, this is the group table in generic symbols A and B. Now I'm going to move on to the octonions because the octonions diverge in the Cayley-Dixon algebra. But what I'm trying to say, what you say?
Well, I'll say the Cayley-Dixon algebra is going through quaternions, octonions, sedenions, and so forth. And each time you break another rule or something, or make it more constricted. And the octonions, of course, break associativity as well as commutativity. Quaternions break commutativity. And the octonions, and we don't use the octonions, but we want to explain why we don't use the octonions.
So you can see you can get all of, if you start with the primary length, which is I'm taking ABC, you get all the product intersections.
I've never seen the octonions presented this way, but it's a neat way of doing it.
And that's just the generic group table for octonions. Okay, now this is something that, this is just basically me working out that these independent triples, which I'm calling also the length, I have to say that, is basically, I'm just working this out to show this, so that yeah, go ahead.
Excuse me, it's not just the octonions, but any sort of number of,
right.
Anything based on this fundamental basis it would have the same structures. It's just what they become when you
interpret them.
Interpret them. And the octonions become something different to the because you get these minus signs and things because of anti-associativity.
Right. Now, right, so here I've just, yeah, you get the minus signs, and this is another, right, so these three independent units form a line on the projective plane if you're looking at the final plane, and they are an independent triple, which means what I'm trying to say is that the independent triple will form a line on the final plane, including the circle generating center one. So that's just another demonstration, demonstrating all the different combinations. Right. Do you want to?
Yeah, just any algebra generated by just two elements will always be isomorphic to the quaternion. It's only when you get three elements that it looks different.
Right.
That's all we need to say.
This is a final plane, of course, in terms of the generic symbols I defined. But Peter has, there's another development that can come about.
Essentially, you could take this as a tetrahedron and do it in 3 dimensions. And this might be a cone pointing to that. And that's relevant to the development of the algebra that we use. Because you can actually, the algebra we use, you can displace the cone, to to connect there to there, and then you will get the algebra that we use.
So basically what we were trying to emphasize here was that the final plane is not confined to octonions. It can be used for any algebra based on 8 units, including the mass, time, charge, and space algebra that is in the Dirac equation in Peter's literature.
Yeah, that's what we were saying. The final, if you interpret it three-dimensionally, you've got 2 4-dimensional objects. You've got quaternion and you've got what you might call 4-vector. And this is what you get when you get the minimum number of generators of the whole algebra.
And that's also Peter's...
that's like sliding that over,
right.
Sliding over the cone, or even another tetrahedron onto, and displacing it.
And this is the gamma matrices in algebraic
That's
form.
the gamma matrices,
yeah. Okay.
You can imagine there being a set of algebras following the Cayley-Dickson procedure, which say like that, and here is the basic algebra, the Clifford algebra that is used in the rewrite structure. And you can imagine an infinite number of combination algebras and other types of grid algebra in between. But this one down here, the one we use, is the minimal representation you can possibly have, the minimal number of assumptions. This one here makes assumption at each level.
And that's just the continuation. If you continue down the Cayley-Dickson line, if you want to call it that.
See, all the algebras will look like this. All of them. It's just
generic,
what these
yeah.
become. It's just what these
you
become.
interpret them, yeah, what they become, and what roles you accept.
Yeah, pluses and minuses and the rest. This is what we've just said.
Yeah, so we can skip this. Now, I've got a category theory phenotype. Basically, the next few slides I'm going to basically just go very briefly because these slides are basically just working out the demonstration. I don't want to say, I'm afraid to use the word proof, but the demonstration that the URS, like I said, if you assume that all of this positive character is condensing all of the positive half of the URS and the negative half, and you put them together, you get a co-product that is a large zero totality, well, the zero totality, where each, like I mentioned, that's just the different components, the sum ends. So I'm going to skip. I'm going to basically.
It's all right. I don't think.
Yeah, I think that. Yeah, I'm just going to show you
just
briefly.
saying that category theory representation is possible because a lot of people are interested in category theory. So we've gone for a category theory demonstration, but this is pages and pages of this stuff. So,
me working it out.
You know, we can't really go through that now.
We're not going to go through all of this.
Just
skip all this. Right.
That will appear in the paper and people can work it out for themselves.
And this is just the co-product. I haven't finished this part yet, so I'm still working it out. Right. Another point last thing I want to say about category theory phenotype is that this is interesting because the conserve rule in the URS can be like the distributive law in category theory, and that's still being worked out. So just move on from there. I don't want to lose that. Now we're on to music.
This is a bit of entertainment. If you say that thing about the concatenation.
Right, so if you concatenate, this is technically order 64, and if you concatenate all of the characters of the symbols of order 64 into one long word, which is detailed in our 2 papers that we wrote, we can apply a musical scale to it.
For example, this could be your 1 and minus 1 I minus I1, I2, then I3, I4, and I1, I2, I2, J2, sorry, I1, J1, I2, J2, and that would be I3.
Yes, G is I2.
So it happens that there are 7 of these, which is just nice because one can present it as a musical scale using any version you want. So you can have it in any key you want. So we have a little bit of music, just this part.
This is just the pattern, the explanation of how we did that, the the musical scale, and let's go back.
Can we play that?
Yeah, we'll play it.
Music?
So this is what it sounds like, and I will be done because that's just now. If you go back here real quick,
Doesn't
that was
sound
just the
too bad,
first
does it?
7. That was just the first. The red is the characters I've put into Muse score. So I've put this, transcribed this into notes, and it's just playing it out.
Yeah, there is a program for doing that, but we still got to do all these yet.
We haven't done the rest of them yet, so.
It's a lot of labour.
Okay, thank you for listening.
Thank you, Sydney.
Oh, sorry, you didn't say that.
Well, you can play it again.
Thank you. Okay.
Well, hang on. Questions?
Questions, yeah, questions.
Can we put the Zoom gallery up?
Okay. Do you want to share the screen still?
Questions,
yeah,
comments
that's fine.
from
No, just
Zoom or
Zoom,
from
yeah.
the audience?
Tear me to parts. I know it's coming.
It's still a work in progress.
I have a lot to do with still working out those characters.
The thing is that this is such a pattern as it can be done in many things. Laws of form is the next, and anything at all. And the idea is to get a version of it in any format that's of interest, because it clearly keeps occurring in nature. It occurs in the Dirac equation, in the genetic code, in particle structures, in 2 different ways, and probably in lots of other things as well.
Yeah. Very primordial. Nobody has any questions?
Nobody question or comments? Mike.
I read some book by Alexander Unziger, and he was saying that the quaternions are interesting because it's a bit like the 3 dimensions of space and the 1 of time. It's reflected in the quaternions.
Yeah, it's the reverse.
Yes, well, you have sort of one thing like time, which is different from the other 3, which are space.
Yes. Yes, well, you can get the 4 vector stuff by simply multiplying the quaternions by an imaginary number. So that converts the real part into I, and then the three imaginary quaternions then become real 3-dimensional objects with exactly the properties that vectors have. In fact, vectors don't make any sense unless you understand quaternion. So it's a disaster that they're not properly taught in courses.
Yeah, and with vectors, our space, I have to say this out loud, but our space is really just, we see it as 3-dimensional, but if you take the full order 16, it's really 16-dimensional.
Yeah, you got vectors, pseudo-vectors, pseudo-scalars and scalars, and plus and minus of each. So you've got 16 units to describe vector space. 3 units doesn't do it. The quaternions only need 8 units. 3 imaginary, 1 real, and plus and minus.
And that's what I was trying to bring across in that generic, writing those algebras in ABCs, because
But
we wanted to show the structure.
If you put a vector with a quaternion, you get what we call the Dirac algebra. And if you put a vector with a vector, you get the Dirac algebra. But you can't put a quaternion with a quaternion, you've got to complexify it as well. You've got to multiply it by I as well.
That's order 32.
That's just over 32, but you multiply it by I, you get 64. And you only need 5 generators for 64. And those 5 generators have the structure which is the same as the gamma matrices. I mean, it's amazingly beautiful, simple. Mike.
Thank you very much, Peter and Sydney and the others who contributed. Referring to some of your earlier work, Peter,
Yes.
You claim that you calculated the percentage of dark matter at some point,
No,
right?
dark energy.
Okay, dark energy, sorry. As you know, since I phoned you when I was really excited about what you called Nature's Code, I took the view that in the, what you might call the anti-space, the one with the hash today, that is where information hides out, with the definition of information obviously being different to the news on the TV or something. Now, is it possible that what you calculated for dark energy is hidden in the hash space, the anti-space?
I think it is in a way, because it is a vacuum effect of some sort. It's a vacuum effect in Mike's presentation as well. Your Unruh effect and your Casimir effects are vacuum effects. That there are quantum vacuum effects. Yeah, it certainly is.
So let's hope that one of us can do a calculation at some point. The idea I put forward when I spoke earlier is that information exists in the anti-space, and using the Zitterbewegung word, which I still can't spell, thank you very much, John, for trying to educate me, it seems that the idea of Zitterbewegung being a very, very basic notion is that everything has two aspects and it oscillates from one state to another.
Yeah.
And the work which I referred to by Pasco says that the actual state, to use his words, is in what you might call the non-hashed version of space, and the other one is in the hashed version, and they just iterate one to another.
They swap over.
So so I'm claiming that this also perhaps gives an explanation for what Mike was talking about earlier on.
I think
which
it's related, yeah.
Go on.
I think it's related.
So, okay. I'm claiming taking what you might call the very high level view and acknowledging that, you know, what you said earlier, that the reason, not earlier, but in another phone call, is that nature deals with quaternions, and that nature is obeying quaternions, as it were. So I'm asking you to contemplate my statement that information is in the hash space.
Well, I think I agree with that. It is there, because if you've got, I've said that earlier in the conference, if you've got quantum mechanics, your information about the past is in the time, the positive time, effectively. The information about the future is in the negative time, which you can't access, except gradually. You can't access it immediately. But it's all somewhere stored in that negative time thing, opposite time direction, and the information that you've got is in the time direction that you're familiar with. And one thing I wanted to say about this stuff is that if you got a vector quaternion or a double vector or anything, you kind of got two spaces. And physically, I say one of the spaces is space as we know it, and the other one is the other three fundamental parameters: time, mass, and charge. And that they together, because there is a pseudo-scalar, a pseudo-vector, and a real number. You put those together, you get another vector. Pseudo-scalar and a vector will make a pseudo-vector will make a vector. So you've got another vector theory. You've got a double one, and this is where you get all these factors of two. You know, Barry phase and all that kind of thing. Everywhere you get a factor of two, it's because you've got two spaces in the universe. And that's what Zitterbewegung is, switching between the two. So it is information switching between the two. But you can't directly access the information over there. You can only indirectly access it. So I think that makes total sense.
Can I just make probably a quick comment that there's perhaps a very simplistic way of looking at this, and it has to do with Zitterbewegung. And if you're just thinking, again, forget quantum mechanics for the time being, just think in two-dimensional space-time, Minkowski, and just take 2 points on the world line. Those 2 points on the world line define the area. Okay, and you know, it really is an area because there's the intersection of the future tone of the first point and the class cone at the second point. And it is those two things that you have to keep within the description. And it is those two things when you sort of put it all together that from what I can see comes up with the time reverse directions of Peter's Peter formulation, and it actually tells you that one of the reasons we have a hard time seeing them is simply that we're in the wrong reference frame. We are large objects, and we think of a special coordinate system which gives us we get from the rest mass. Well, to create a rest mass, nature, the way nature has to do it, it has to look along in any plane the two null directions. It requires those two. And so the way nature counts is not really 1, 2, 3. Nature counts with these two directions in a two-dimensional space. And when you look at that, then you can begin to see where does it they can come from. In a sense, it's simply the way nature counts.
I remember saying to you after your presentation, is the area in principle implying angular momentum? Because that's what it does. And you said yes.
Yes, it does. And there's this nice, very pretty conspiracy between the angular momentum and the going back to Newton and saying, okay, we're really in this sort of flat space-time where space and time are independent. And when you look at that and you start playing with diffusive powers, which we all understand from diffusion, you look at that and say, well, how do you get the diffusion equation out? Well, the way you get the diffusion equation out requires everything to be flat, space and time to be independent, and you automatically on the lattice have these two directions. But the way the numbers work out is simply that when you do the refinement of the lattice, you have this funny term, delta x squared divided by delta t. And that goes to a constant as you take the limit. So that is the signifier of the angular momentum. And the way that's taken care of when you actually add in Minkowski space is the Poisson process has this other funny feature where you look at the expected value of the number of corners, and then you look at the expected value of the variance, and they're just proportional. So you have the two things balancing one, which comes up time and time again in Peter in your work. Right? It's always the two thing.
Even half mv squared is the same factor. Even half mv squared is the same too. And
yes,
and even half base times height is. Yeah.
Yes.
It's all the same too, from the same thing.
Can we refer to words a little more? I've in the past had the pleasure of speaking to Carl Prevran, and I asked him if he had thought about where information is stored, and he said we don't really even have the beginnings of a theory, but he did say, and he supported in some of his writings, the idea of holograms. So trying to refer to what I call the hash space or the anti-space in Sidney's speech, that's one possibility.
The holographic principle as well, bounding area.
Right. So the what I think is perhaps giving clarity on what the equation means is to focus on the hash space a bit more and figure out what's going on there. Now the other work, which is revealing a different part of my life, I work with some healers whose basic notion was that everything is completely recorded, and if you were working with a patient, you could access the information related to them before they became a patient, i.e. not a normal or healthy person, and then you could work on the traumatized part of the record and correct the person, and eventually the person's body would construct its cell structure to be consistent. All that on the healer side is very interesting, but it does point to this idea that time has no meaning in the hash space. I don't know if that's what you said, Garnet, because I got lost at about the second delta.
Well, actually, that's very close to it, and you can see this if you just ask yourself the question. Basically, how does nature know? So take 2 points on a world line, right? 2 points in time, and what I call the causal area between them is the intersection of the future code and the past code. So if you have our usual time sense, you have to say, well, okay, you're going from the bottom of the past cone up to the top of the past cone. Sorry, you're going up the future cone from the bottom, and you have to reach the next event up here.
Close it down.
How do you know in the middle where the heck the next guy is? Like there has to be in that some sense of preconditions
The program first.
to figure out where the point is further up between the two intersections. So what that is saying, and what the Dirac equation is essentially saying is between those two special points, the distance of which is defined by math, the time itself is not as we think of it. It's not going, simply 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The nature has to have a special way of getting the next point, and it's not a simple translation, which in classical physics it always is. It's always a simple translation of going along the world line, just step after step, and the steps can be as small as you like. As soon as you put that periodicity in, then the whole idea of anticipation comes in. So I would say yes, that this is an indication that time on very fine scales does not work in the way we think of it.
There is.
Then we think.
Sorry.
Sorry.
You carry on. I've got some.
How much time do we have to talk on this subject, Sydney and so on?
Well, we're okay because we're not finished the time slot for this.
Okay.
I was going to say.
Sahu has a question.
I think Albrecht.
Also, I have quite a short presentation, so just carry on.
Okay, can I just say about something connected with that? I mean, the way we see Zeta Bewegung is that there's no such thing as straight line motion of a particle in time. At velocity v, it's travelling at c all the way, zigzagging all the way. And it only averages out to v over a straight line.
I think Albrecht had a question.
Yeah, Albrecht.
Yeah, I think Albrecht has been speaking, but he's on mute.
You're on mute.
Can you?
We can't
Somebody
We can
asking
hear
me.
you now.
Ah, yeah.
Go ahead.
Okay now.
Okay.
Well, what was your question to me?
No, I
Have
thought
you
you
got a
had a
question?
question. Did you have a question?
No,
I didn't ask a question. I could make
No problem.
I could make a remark or comment to the word, to the term, what is this noun Zitterbewegung, because I think this is greatly misunderstood. I think I have a good knowledge of, well understood what Schrödinger meant by it, but I perhaps have the occasion to talk about that in my talk.
Yeah, well, wait till you talk about it in your talk, and then we'll find out. Sahu.
No, that was all.
He was just saying Albrecht had a question.
Okay, I think we should take a short break then now.
Hang on, Peter, I got one more line of thinking to distract us from equations. Have you encountered the root idea of the people who believe that the universe is basically exercising computation?
Well, what does that mean?
That's Wolfram.
Yeah, Wolfram.
That's right. That's Wolfram's reason. recent thing seems to be indicating that, which basically, you know, if you're listing all the phenotypes of various pieces of the maps of theories we have, that needs to be added, or maybe it's a meta idea.
Well, I think that that particular basis of basing everything in computation is sort of half the picture, because it's discrete. It's putting the primarily discreteness as like the main description, defining characteristics. So I think that might be...
That's one of the two spaces. The other one is the... Yeah, he doesn't see... The way I see things is you've got a system, whatever you define, and then you've got everything else. And it's the interaction between those. And they are mirror images of each other because they combine to zero. And they also multiply to zero because they're each nilpotent. Now, I don't think...
Oh, I will say that by that, I wasn't talking about nilpotents when I put that, when I was talking about products. That's a certain order of the rewrite systems. I don't want to get people confused.
Yeah, that's that fivefold thing.
That's the fivefold that multiplies to zero.
I don't think Wolfram thinks in those terms.
No, he doesn't think in terms of...
Yeah, and I think you can only get so far with the computational model.
Yeah.
But one thing that I'm going to do, well, I've done it already, but have not presented it here, is I've used Wolfram's cellular automata, and you know, that's another model. And it's possible to use that, but not all the cellular automata, only the ones that matter within it.
Yeah.
But just the four that are Turing compatible.
It's very interesting because this rewrite system is very specific. It doesn't just accept anything.
Yeah,
It's not just generic. It's not generic in that way, but it's generic in that its power, but it accepts only specific components.
It doesn't accept everything.
As its building blocks.
Another comment directed at, in a sense, what Garnet was talking about. If the procedure that nature is carrying out because of maybe the actions or thoughts of living systems, if it's got, in a sense, a sort of computational notion, then there might be something like error correction. And there seems to be a feeling among people who...
That's the conserved part.
That's the conserved part.
That's the conserved
I'm not speaking in
that form, okay.
quaternion or formal language there. I'm talking about subjects which are much more into biology and so on.
Oh, okay.
So the idea that nature, let's say, host life on planet Earth contains something which is in a moderately accurate sense alive, and it proceeds, and every now and again there are branches, and you can imagine the idea of the primates emerged from something before, and the primates give birth to something else, maybe it includes humans and so on and so on. The point here is that every now and again it goes down the wrong path, which is then rejected. And the path, if you like, the error correction is to ignore that which can't be included. So if we go back to your alphabet thing, it strikes me that that notion that the reason you've chosen the particular level 6 is right, is because up until that point, everything that has been, as it were, alphabetized is included in the next one. And so a big leap is when you double the entire alphabet space and so on. And it strikes me there's an analogy there with the way that nature goes, and we can use that as guidance as to how things work in the, what I call the hash space or the empty space.
The reason why we use level 6 is because we get zeroing, a special zeroing at that point. And that's what we're always after. And if you can use higher levels as structural things for other things, but you always get that level 6 as being the key thing.
In fact, that's the level at which it converts into, you could convert it into a Hilbert space.
Yeah, you can do multiple things after that.
With commutative coefficients.
Garnet had a point or
Oh, yeah, go on.
question. Garnet, do you want to say something?
Well, yes, and it's again to do with this. I mean, we still sort of bandy about a bit about, well, you know, are things continuous? Is it all real numbers or not? And I've been a bit insistent that we have to think about things that we can actually count, because in the end, the whole idea of real numbers is beautiful, but it's completely unreal. And of course, when you look at the Dirac equation and all of your calculations, Peter, you know that the mass means that there is a finite countability to everything that comes up, and the real numbers, in a sense, fill in and give us a way of averaging, which is, of course, the way our senses work anyway. We always just detect averages, so we think in terms of averages, and so real numbers are appropriate. But in the end, there is a discrete aspect that your stuff is picking up, right? I mean, the way you describe it through the Dirac algebra. I mean, Dennis did a very nice job of the conjuring trick, where he started with the real numbers, and he quietly slid in I sigma y. Right? That was the thing that actually starts up the whole process and says, no, actually, you have to have these two processes that we can switch between that give us the clocks. Right? So if you do it inaccurately, you can just bring in the square root of minus 1, and you can end up with the Schrodinger form. But as you point out, Peter, it doesn't do a great job. You really do need the Dirac algebra.
Oh yes, you can't do it without Dirac.
Yes,
you can't do it without.
And it is really Dirac that brings back in the discrete aspect, right? The Dirac equation says you have a mass, and associated with that mass is a frequency, and that frequency, if you translate that back to position space, right? You say, oh yes, that we have this the equivalent of mean free time, which is the Compton time, and so the events that we associate with that are now back to being counted. And so we can sort of deal with it. And then we go back and say, well, our language is too difficult to do the accounting if we stay discrete. The language is much better and simpler if we bring in the whole kit and caboodle, which means bringing in real numbers.
You know, there are two sets of real numbers, one of which is countable and one of which isn't. And there's the non-countable one's the Cantor argument, and the countable one's the Robbins argument. The what do you call it? Loewenheim-Skolem theorem. Denumerable. So there are real numbers that are countable. The ones that you did find an algorithm for doing those real numbers, they're countable. If you just do a Cantor type argument, they're not countable.
Well, okay, you can define processes whereby you can get access to real numbers, but the real numbers themselves are not countable.
No, but they are. It depends how you describe the real numbers.
The easiest way I can describe real numbers is a continued fraction. You use a continued fraction. You have a fractional form. It's all part of discrete
countable
elements, but you have to buy into this idea of infinite. Like if you have an infinite way of representing a fraction that's branching out forever, or you have a way to describe it, that's giving you real numbers. So it's really in a discrete form, but you have to buy into the idea of the infinite, like an infinite process that's going to get you closer and closer and closer and closer to pi. So if you buy into that, then sure, you have the real numbers. So in that sense, that is the easiest way I can say what a real number is. I mean, it's a continued fraction with discrete elements.
Yes, absolutely. You can build these processes, but just to sort of make your confidence in real numbers maybe a little bit weaker, think about fractals, right? you can take a smooth continuum and make it smooth down to an arbitrary, 10 to the minus 1 million centimeters, and then you play a trick and say, okay, well, from now on, there's going to be a space-filling curve for Ecuador, right? I mean, from that perspective, the smooth continuum that we use, it's fabulous for doing calculations. It's very good for taking care of bookkeeping, but there are lots and lots of alternatives, and it's a language that maybe we should remember is there for convenience.
Well, there's a difference between infinitely divisible and what's the other one? The absolutely continuous. Absolutely continuous is completely different at the opposite end of mathematics to infinitely divisible. But we use both for describing real numbers.
It's like if you think of Peter's parameter group, you got time as the continuum, and then you've got space as the algorithmic real number. Time is a continuous real numbers and space is an algorithmic.
Yeah, I use both sets of real numbers.
He uses both.
Yes. I guess one way to see it from in the mathematical literature, there's always been this thing, mathematicians tend to get annoyed with physicists for still using things like differentials because they're very, very useful, right? We use them all the time and it colors our thinking, but of course you can't build the differential from points. Okay, that's the.
But there's no such thing as points.
Well,
the mathematicians, make up things. No such thing as points. You draw me a point.
Yeah. Well, okay, exactly. But then look at the standard relativity. What is an event? Oh, well, it's a point in the world, right? So you sort of have this embedded in the language.
They talk about a point in a line, and you can't even draw a line
without 3D space.
You can't draw a line without 3 dimensions.
Well, that's right, and that's why I say we just have to be a little bit cautious about some of these assumptions that we use routinely. And I mean, in your work, Peter, the whole idea of, I guess if I have a complaint, it's a complaint not recognizing the fact when you go to the Dirac algebra, it's not just real numbers. I mean, the thing that makes it work is the algebra itself, and the algebra.
It's all about algebra.
You can check that. You can take it back to the structural space.
The only thing that matters is the algebra.
Yes.
Yeah, yes. That's the only thing that matters, isn't it?
Yeah, I think that's right. I'm a bit confused. I seem to remember when I was still studying maths.
I know, we got kind of diverged off of this conversation about...
But anyway, just let John...
Go ahead.
And then we'll close the discussion.
Yeah. Am I wrong here from people who know more about maths than I do? But aren't there numbers that can provably, the so-called, are they transcendental or transcendent numbers, things like e and pi, that cannot be expressed as a continued fraction or in any other way that can be proven to be between those numbers? Is that? I seem to remember doing a proof for one of those. You might have been pi.
No, there is a continued fraction expression for e, for pi, for all irrationals, but it depends on if you're using a finite chunk or an infinite chunk. So it depends on that. If you have a finite continued fraction, or if you have a long, infinite continued fraction that has. So then you're getting closer and closer and closer. You're approximating to this.
Yeah, but that's different to. But one can, I think, prove that things are not. That whatever degree of precision one takes, one can always take the next one, and find that changes a little bit, and hence the process is unending. Is that not true?
Not for these numbers. No, they are definitely describable in that way.
Yeah, they're describable by continued fractions.
Just as you can...
Pi is describable by continued, like the golden ratio is describable by continued fractions. Everything, I mean, all the irrationals and rationals, you can describe it by continued fractions, yeah.
All the ones that you can talk about.
Yeah.
But you can imagine an infinite continuum of numbers that you can't describe that way.
Yeah, absolutely.
Yeah. Anyway, I think we should close this very interesting discussion and give people a break for a few minutes.
Yes.
And then we have Barbara's going to talk. But we're going to start things up a bit earlier this afternoon. Everybody be warned that we're going to start at 2:30 because we need to leave the building earlier than we thought. Okay?